Dear student, warm welcome to NPTEL Phase 2 program video course on geosynthetics engineering in theory and practice. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. This lecture number 52, module 11, designing with geotextile tube. So I will now focus the recap of the previous lecture, that is introduction, geotextile tube, geotextile container, geotextile bag, dewatering of waste contaminated sediment and geomembrane dam. Now I will proceed for the hanging bag test. You know, geotextile tube encapsulated the soil that may be used to replace the rock as conventional building block in marine and the hydraulic structure. And this concept is not new. Many people have used the jute bag filled with the sand to protect the dam from flooding. And this kind of geotextile bag or the container or geotextile tube can be extensively used for the shore protection, erosion control, dewatering of municipal sewage, sludge and drinking water treatment plant and the agriculture and the agricultural ponds. So this kind of technology is not very expensive and it is easy to treat the sludge or the slurry. So hanging bag test is not reported in India so far in my knowledge goes. So present study addresses the performance of hanging bag test for dewatering of different type of the slurries. It may be the fly ash, it may be power soil, it may be the marine clay. Also, apart from this, we have also performed the environmental analysis of this study before and after the test have done to check the efficacy of the dewatering system in removing the contamination from the slurry utilizing the geotextile tube. Now a hanging bag test is conducted to assess the suitability of various geotextile fabric with respect to site specific soil. The proposed test method in accordance with GRI GT 14 code in 2004. Hanging bag test is conducted to determine the discharge of water through the geotextile fabric over a specific time period. Designer must conduct the hanging bag test prior to the fabrication to approve the geotextile fabric for a particular site. It is not so easy that if you know only the apparent opening size of the geotextile, it will satisfy this criteria, but it is recommended that one should also proceed for the hanging bag test. This is very important for the selection of the proper kind of the geotextile tube. So, we have performed some experimental program on 3 types of the soil was selected for the hanging bag test, that is one Powai lake soil, fly ash as well as marine clay. You can see this figure, Powai lake, this is the fly ash and this is the marine clay. And some properties of this Powai lake sediment, fly ash and marine clay are reported in this table, and moisture content we take about 341% for Powai lake, 305% for fly ash and marine clay 356. Organic content for Powai lake 2.41%, fly ash 0.1035% and marine clay 1.874%. Specific gravity for Powai lake 2.74, fly ash 2.18 and marine clay 2.65. Liquid limit Powai lake sediment is 54.3% and marine clay is 54%. Plastic limit for Powai sediment is 30.8% and marine clay 31%. And D10 and D30 and D50 for the gain size distribution curve, I will show you later. That is D10 for fly ash 0.003 and marine clay 0.0016, D30 is for fly ash 0.014 millimeter and marine clay 0.0025 millimeter, and D60 for fly clay 0.035 millimeter, fly ash 0.045 millimeter and marine clay 0.0061 millimeter. So, also that soil properties continue, this optimum moisture content for Powai lake 23.60%, fly ash 23.02%, marine clay 29%. Maximum dry unit weight is for Powai lake 18.56 kilonewton per meter cube, fly ash 11.92 kilonewton per meter cube and marine clay 13.7 kilonewton per meter cube. Cohesion for Powai sediment 54.3 kilonewton per meter square, fly ash 3.3 kilonewton per meter square and marine clay 62.72 kilonewton per meter square. Angle of internal friction angle for Powai sediment 19.14 degree, fly ash 15 degree and marine clay 5.24 degree. So, these are the grain size distribution curve for the Powai lake, from where you can calculate this value D10, D50, D60 or CUCC. This is the curve between the percentage of filter and the particle size. This is the gradation curve for Powai lake. Next, this is the gradation curve for the fly ash. So, from this curve also you can calculate D10, D50, D60, whatever the parameter you require, CU and also CC. And this is the gradation curve for marine clay. This is the particle size versus percentage of finer. So, from this, all this curve you can calculate this property, basic property. Now, apart from this gain size distribution curve, also compaction curve for standard Proctor test also have been performed, and this is the compaction characteristics of Powai lake soil. This is the maximum dye density versus the moisture content. So, you can calculate what will be the maximum moisture content and the corresponding the maximum dye density. This is the compaction characteristics of the fly ash. This is maximum dye density versus water content. So, you have calculated the water content and corresponding the maximum dye density. And this is the compaction characteristics for marine clay. So, you can calculate what will be the maximum water content and corresponding the dye density of marine clay. Now, also we have performed the chemical properties of the soil, that is X-ray diffraction. So, for Powai lake soil, that is quartz and zeolite, fly ash, mullite and the silimarite, and marine clay, silicon oxide and hamilite. So this test has been also performed in MEMS in IIT Bombay. So this is X-ray diffraction curve equipment. Now this is X-ray diffraction image of the Pi lake soil. You will be knowing how is the characteristics of the X-ray diffraction image for Pi lake. This X-ray diffraction image of this fly ash, this X-ray diffraction image of the marine clay, chemical properties of the soil, carbon, hydrogen, nitrogen, sulfur, CHNS test. This test has been performed is SAFE IIT Bombay. This is the equipment has been used. Now Pi lake soil, that carbon is 1.225 percentage, hydrogen 0.044 percentage, nitrogen 1.362 percentage and sulfur 0 percentage. Fly ash, carbon 0 percentage, hydrogen 0.669 percentage, nitrogen 1.409 percentage and sulfur 0 percentage. Marine clay, carbon 0.792 percentage, hydrogen 2.401 percentage, nitrogen 0.264 percentage and sulfur 1.58 percentage. So this is the chemical properties of the soil, X-ray fluorescence test. This is the equipment has been used and this is from SAFE IIT Bombay, and from this test we can obtain that oxide, that what will be the value for Pi lake soil, value for fly ash and value for marine clay. So Al2O3 for Pi lake 14.329 and for fly ash 24.643 and marine clay 15.284, BaO Pi lake 0.035 and fly ash 0.091, CaO for Pi lake 2.568 and fly ash 1.048 and marine clay 3.773. Fe2O3 Pi lake 14.861, fly ash 6.437 and marine clay 13.555. K2O for Pi lake 0.493, fly ash 1.047 and marine clay 1.640. MgO 3.424 for Pi lake, 0.788 for fly ash and 5.585 for marine clay. MnO for Pi lake 0.271 and for fly ash 0.049. Na2O for fly ash 1.188 and for fly ash 0.120 and marine clay 3.662. P2O5 for Pi lake 0.029 and fly ash 0.103 and the marine clay 0.202. SiO2 for Pi lake 55.832 and fly ash 61.111 and marine clay 49.7373. SO3 for Pi lake 0.043, for fly ash 0.032 and for marine clay 0.525. SRO for Pi lake 0.048 and fly ash 0.064. TiO2 for Pi lake 2.205, fly ash 1.467 and marine clay 1.437. So this is the Canning electron microscope. This is for SEM physics IIT Bombay, and you can see here that SEA image of the Pi lake soil at different magnification. This is from the physics department IIT Bombay. You can see that what will be the size and the shape of the Lake soil. What is the micron effect for this soil and how it looks. Similarly, this is the ACM image of class A fly ash at different magnification. So, this is the for 5, this is for the 20 micron, and this is the ACM image of the marine clay at different magnification. This is Physics Department IIT Bombay. This is for the 20 micron, and this enlarged form about 50 micron. See that how there is a formation of the void also in this soil. So, apart from these soil characteristics, also we should understand the behavior of the geotextile properties. So, two different geotextile was selected. One is the woven polyester multi-filament geotextile and the woven jute geotextile. So, this is the Canning electron microscope ACM image for the woven polyester multi-filament geotextile at different magnification. You can see here what is the filament. This is the woven geotextile material multi-filament. So, enlarged form, these are the filament form in 200 micron. This is the ACM image of the woven jute geotextile at different magnification. So, you can see here in a magnification form how the filament, all the filament are almost perpendicular to each other. So, from this we have also performed the properties of this material, that is the thickness as per STMD 5199, that is woven polyester multi-filament is geotextile is 0.0975, for woven jute geotextile 1.90, mass as per STMD 5261, this is for woven polyester is 338 gram per meter square and jute geotextile 670 gram per meter square. Permittivity STMD 4491. Now, for the woven polyester multi filament geotextile 0.0224 and jute geotextile 0.103. Apparent opening size as per STMD 4751 for woven polyester geotextile is less than 0.075 millimeter and for jute geotextile 0.131 millimeter. Wide width strength as per STMD 4595, there is a wave and wrap direction. Wave direction for polyester geotextile 48 and wrap direction 136 kilonewton per meter. In case of jute geotextile, OFT is 19 kilonewton per meter and wrap direction 24 kilonewton per meter. And corresponding strain as per STMD 4595 for the polyester geotextile in wave direction 13%, wrap direction 8%. In case of jute geotextile, the wave direction 10% and wrap direction 9%. Trapezoidal tear as per STMD 4533, that is wave direction 0.38 kilonewton per meter, wrap direction 0.75 kilonewton per meter. And for jute geotextile, in the wave 0.73 kilonewton per meter and wrap direction 0.71 kilonewton per meter. Now, apart from this property, we have also performed the puncture strength as per STMD 4833 for polyester. This is 0.95 kilonewton, for woven jute geotextile 0.38 kilonewton per meter. Graph strength as per STMD 46632 in the wave direction for polyester geotextile 0.86 kilonewton and wrap direction 1.2 kilonewton. For jute geotextile, then wave direction 0.64 kilonewton and wrap 0.78 kilonewton. And UV resistant percentage as per STMD 4355 in the woven polyester is 68% and the woven jute geotextile is 56%. So, this is the wide width strip test, that is for woven polyester multi-filament geotextile. This is the wide width sample. This is about the 200 millimeter the width and 100 millimeter is the gauge length, and this is the test for the wrap direction. This is the before the test as per STMD 4595 and you can see the after the test in the wrap direction as per STMD 4599. This is very typical failure of the woven polyester multifilament geotextile in the wrap direction. Similarly, this wide edge test also I have performed in the wet direction before the test, and then this is the after the test. You can see that what will be the nature of the failure of the woven geotextile in the wet direction. Now, this is the wide edge tips test for the woven jute geotextile material. This is wide edge sample in the wrap direction before the test as per STMD 4595, and you can see that this is the failure of the sample after the test of jute geotextile. It is very typical nice failure of jute geotextile. This is in the web direction, this is the before the test and also after the test. So, trapezoidal TS test, this is woven polyester multifilament geotextile. This is strength about 0.75 kilonewton per meter in the machine direction and strength 0.38 kilonewton per meter in the cross machine direction. This is trapezoidal sample in the wrap direction, this is the trapezoidal tear sample in the web direction. And similarly for woven jute geotextile, this is also the trapezoidal tear sample in the wrap direction, and this is in the trapezoidal tear sample in the web direction, and strength is 0.70 kilonewton per meter in the machine direction and strength is 0.71 kilonewton per meter in the cross machine direction. This puncture strength state, that is woven polyester multifilament geotextile, strength 0.95 kilonewton. This is puncture strength sample before the test STMD 4533, and this is the puncture strength sample after the test. You can see here there is a formation of the whole of the sample polyester geotextile. Similarly for jute geotextile also puncture strength has been performed and puncture strength is 0.58 kilonewton per meter. This is before test and this is after test. Graph strength test, also graph strength sample in the wrap direction and graph strength sample in the web direction, and graph strength value is 1.2 kilonewton in the wrap and graph strength 0.86 kilonewton in the web direction. This is for woven jute geotextile. This is the graph strength sample in the wrap direction, you can see very typical failure, and also this is a graph strength sample in the web direction. And the value for graph strength is 0.78 kilonewton in the wrap direction and graph strength is 0.64 kilonewton in the web direction. So, all these tests has been performed in our geosynthetic research and testing laboratory. So, now I will proceed for the hanging bar test at Das and Mandal 2012. Now, a geotextile bag is fabricated by sewing a fabric along its bottom part and along the side. The butterfly stitching technique is selected for this purpose. The selection of stitching technique is important to ensure no tearing of the bag after filling it with waste slurry. The bottom part of the tube form an enclosure in which the slurry or the saturated infill material is poured in a major amount. Now, this is the schematic of geotextile tube before the fabrication and this is the after fabrication. I can show you here that this is the geotextile tube and this is about 107 centimeter and this height is about 163 centimeter and this is 22.5 centimeter and this part is 8 centimeter, this is 2.5 centimeter, this is 2.5 centimeter and this is geotextile is the seam, this is the seam line, this is the hot outer edge and this is the fold line here and it looks like a kind of cylindrical. This is the closed end and this is the open end. So, in the closed end this has been seam edge and also that one side it has been also seam edge and this length of the geotextile tube is 152 centimeter and this is the open end this is 102 centimeter circumferences. So it was like this, that it is a fabric, it is made of the polyester woven and also the jute geotextile material. It is like this in the cylindrical in the shape. So this is either the jute geotextile or the woven polyester geotextile, and this part is been swing, this side also swing, and butterfly swing has been adopted, and also the bottom part also has been swing, this part also has been swing, and this sari has to be inserted into this geotextile tube from the top. So this is a kind of the geotextile that bag we are talking about, and so leveling and this is the hanging bag test setup is performed to ensure proper alignment. It is required to get the appropriate reading. Now this is the leveling of the hanging bag test setup. So you can see that this is made of steel. This is a kind of the frame which has been fabricated and also developed. So this is the from frame, and this is about 60 centimeter and this is 200 centimeter, and top is this is 70 centimeter, 70, 70, 70, and there is a hole, and this is diameter about 33 centimeter, and this is all the steel iron frame, and at the bottom there is a pan where that when through the geotextile tube the slurry will pass and the water may come out from the bottom of the geotextile tube, and you are to be collect at this pan. So this is the nozzle for the collection of the discharge from the geotextile tube. So this is the leveling of the hanging bag test up. So proper alignment also required. So I will show you that more picture, that how you will perform the test and how you will install the geotextile tube into this frame. So here you can see the leveling of the hanging bag. This is the setup, this is the frame, okay, and this is about 70 centimeter, and this is the circle is 33 centimeter, and here this one is the 60 centimeter, and this from top to bottom is 200 centimeter, and this to here is 25 centimeter, and here you can the pan, and here the hole to hanging the geotextile tube with the help of 8 metal nuts here. So you can see later very clear picture about this 8 metal nut here and how the geotextile tube is hanging from the top of this opening side of this frame, and this is one ladder is used. So this is provided to pour the slurry on the top of the geotextile tube. So you can climb up and can stand and can pour the slurry onto this to this open or to this geotextile tube. So here you can see the student, this went up and then it be pouring this slurry into this tube. So this is the tube. So this is the wet geotextile bag, it attached here to the hanging bag test setup with the flange system consisting of 8 metal, here is the 8 metal bolt attached at the top of the hanging bag test setup. Now metal bolt were provided to ensure proper alignment of the hanging bag. Next, after hanging the bag, you require for the preparation of the slurry. So about 30 kg desert sediment from Powai Lake is collected and mixed with 90 liter of Powai Lake water with the help of a stirrer, and preparation of the slurry involve water to solid ratio, that means W by S to be equal to 3. So, with this proportional, this mixture has been made. So, you have to prepare the slurry very carefully, and then the alum is used as a coagulant, and the solution is prepared at a dose of 133 ppm. The optimum amount of coagulant alum is determined in the laboratory by adding 10 ml, 20 ml and 30 ml of alum to the slurry. Finally, 30 ml of alum is added to the slurry and agitated with the stirrer to obtain the slurry of uniform consistency. This is very important, that you should prepare the sample with the uniform consistency. So, you have to check that what amount of the alum is to be added to the slurry in order that you can prepare a proper uniform consistency of the slurry. Here you can see that this is the stirring and that they are preparing the slurry, and this side that how the sample at the bottom, how the water have been collected and stored in a tube. So, here this bucket filled with the pre-mixed soil slurry was lifted to the working platform in a controlled manner, and time spent to fill this geotextile tube was noted for further calculation. So, this is important, because when you are pouring, then you have to also measure the time, that what time, how much time it is required, because you are measuring how much water can discharge from the geotextile tube and at a particular time. Here students are pouring this slurry into this geotextile tube. Now, a stainless steel plant, here the stainless steel plant of 175 millimeter depth and 60 centimeter of diameter is placed under the geotextile tube to collect that effluent water with some of the fine sediment, after the geotextile tube had drained itself to the free water. So, slurry volume is reduced in the tube because for dewatering, and here you can see that how these 8 nuts here is joined geotextile tube on the top. These are the 8, 1, 2, 3, 4, 5, 6, 7, 8, and this geotextile tube is hanging. So, this is the slurry volume you can see how it is reduced in the tube because of the dewatering, and water is dewatering at the bottom, and there is a span, and you are collecting the drained water which is coming out from the geotextile tube. Now, record the time when the water level dropped by 7.5 centimeter, and continue to record the time for every 7.5 centimeter increment till the water level in the bag drops from its initial state to a height of 72 centimeter, or water stop draining from the geotextile bag. Now, filter it at 1 minute, 10 minute and 30 minute are collected in the seal bottle to check the dewatering quality through the geotextile fabric. Filtrate after dewatering of the sediment or dredged material was collected to conduct the environmental test, and observation were made by comparing it to the sample collected before the test. So, here you can see that filter before the test, that is dirty water at the left hand side. On the other hand, you can see after the dewatering of the sediment, that is the clean water at the right side. So, you can directly have a very clean water when this slurry will process to the geotextile material. Because we use lot of slurry and then you require for the very clean water, it takes lot of time, a lot of machinery, manpower, and the power is required to make the clean water. But here by the use of the geotextile tube, you can directly have the very clean water. So, now collect the sediment passing the geotextile fabric and store in a stainless steel pan during the entire test and conduct the gain size analysis. Cut the geotextile bag to examine the filter cake retained inside the tube. Here you can see that is cut it the geotextile tube and then this is the filter cake. This is the formation of filter cake block. The opening of the geotextile tube and reduce its discharge capacity. So, a representative sample was collected from the mid height of the dewatered soil material to determine the moisture content and the density in the laboratory. You have to check what should be the moisture content, what will be the density. Now, this is the some test result from the hanging bag test. So, water level, as I say that you can start from 7.5 centimeter, then 15, 7.5 meter interval and up to the 72 centimeter. Okay. So, you can continue and then you are measuring what is the elapsed time, that is TE in minutes. So, when 7.5 it takes 2.24 minutes, after that 15 centimeter it takes 9.30 minutes. So, when the water level drop at 22.5 centimeter, then that elapsed time is 23.29. When water level drop 30 centimeter, then your elapsed time 41.10 minutes. And when water level drop 37.5 centimeter, then the elapsed time 77.20 minutes. Now, when water level drop 45 centimeter, then elapsed time 138.31. When water level drop 52.5 centimeter, then elapsed time 221.56 minutes. When water level drop 60 centimeter and elapsed time 340.43 minutes. And at the end, when water level drops 72 centimeter, then elapsed time 1060.23 minutes. So, we can see that how it takes time is increasing with the increasing the drop of the water level. So, from this also we have to calculate that what is T of I. So, Ti is the initialized time, that means that will be the Te minus T0. So, T0 means time to fill the bag, it takes 9.50 minutes. I say that when you are filling the bag, you should also note the time. So, T0 time to fill the bag 9.50 minute. So, Ti will be, so we have to calculate the Ti. Ti means Te minus T0, that is initialized time. So, this Ti will be equal to what is T 2.24 minus the T0 is 9.50. So, 2.24 minus 9.50, which will give T of I is minus 7.26. So, next your 9.30 minus 9.50 is give minus 0.20. Now, next 23.29 minus 9.50 is give 13.79. Then 41.10 minus 9.50 is 31.6. 77.20 minus 9.5 is 67.7 minutes. Then 138.31 minus 9.50 is 128.81. Next 221.56 minus 9.50 is 212.06. Next 340.43 minus 9.50 is 330.93, and at the end 1060.23 minus 9.50 is 1050.73. So you can calculate that what will be the initialized time. Now what is T1 dash? That is modified initialized time. So initially it is the 0, and next is 7.26 minus 0.20. So this is 7.26, this will be equal to 7.7. This is initially it is the 0, so this will be equal to 7.06. 7.26 minus 0.20, 7.06. So minus minus plus, so this 7.06. Now next is this is 13.79 plus 0.20, that is minus 0, that means plus 0.20 plus 7.06 will give 21.05. Now similarly 31.6 minus 13.79 plus 21.05 will give 38.86. Now 67.7, this minus 31.6 plus 38.86 give 74.96. So similarly 128.81 minus 67.7 plus 74.96 will give 136.07. Like that you can continue and you can obtain at the end, that is 1057.99. So this is the TF is the final. So this is the TF final is this is 7.06, and after that this is 21.05 minus 7.06 will give that what is 13.99. Similarly 38.86 minus 21.05 will give 17.81. Similarly 74.96 minus 38.86 will give the 36.1. So similarly you can continue and you can calculate what should be the incremental time. So you know that at this water level drop, and you are also at the same time you are measuring that how much water has been collected from the geotextile tube at a particular time. So from that you can calculate what will be the flow rate. So here that flow rate at this level is 14.66 centimeter cube per second, and then gradually you can see that flow rate is reducing 7.27 centimeter cube per second, 5.81 centimeter cube per second, 2.86 centimeter cube per second, 1.69 centimeter cube per second, 1.24 centimeter cube per second, 0.87 centimeter cube per second, and 0.14 centimeter cube per second. So you can see that what will be the water level drop is water level drop also is increasing, and whereas this flow rate is also gradually is decreasing because for sedimentation or precipitation of the slurry itself. So from this table, so you can draw a correlation between the flow rate in centimeter per cube versus water level drop in centimeter. So, this is the figure has shown the relationship between the flow rate and water level drop during the hanging back test. So, from this table, and if you substitute this value, that is the flow rate value, you can see starting from 14.66 and the water level drop is 15, and this is the water level, this is 14.6 and then 15, you can see somewhere here. So, this is the flow rate versus the water level. Like that, you can substitute this value for the water level drop 22.5, then your flow rate is 7.27, like this 7.27, you will be getting this point, and then again for 5.81, that is in 30 water drop, 5.81, then you can see water drop about 30, and similarly for this 37.5, and this is flow rate is 2.86, 37.5 and flow rate is 8, and like this you can continue and you can have a correlation between the water level and the flow rate. So, from this curve we have observed that how the flow rate is decreasing with increasing the water level, and after a certain drop it has went up to the 72 centimeter and 0.14 flow. So, this is almost 72 and 0.14 flow, this almost that flow is diminishing. So, there will be almost negligible flow. So, you can obtain a relationship between the flow rate and the water level drop. Here how the flow rate is decreasing with increasing the water level dropped. Now, Koenig 2006 and 2010 and Lec-52 et al. 1996 and Pilarsky 2000 and the Hedebound 2010 carried out the various experimental and numerical analysis on geotextile tube. Also, we have also performed some numerical analysis also on geotextile tube. The hanging back test is very much useful for the proper selection of geotextile tube, as the dewatering flow rate can be achieved. So, hanging back test is mandatory for the design of the geotextile tube. The large hanging back test can simulate the field test. Prior to the successful construction, at least 2 or 3 hanging back test is recommended for the quality control and the quality assurance. Now, from this test we have also performed that some environmental analysis. So, environmental analysis of the slurry before and after the hanging back test was performed to check the efficacy of the dewatering system utilizing geotextile tube. So, inductively coupled plasma atomic emission spectrogram ICP AES is an emission spectrophotometric technique utilized to find out the amount of element present in the slurry before and after the hanging back test. So, these are the results from the environmental analysis. This is amount of the different in ppm present in the slurry sample. This is the sample name. The sample before testing, the tube oven jute with the marine clay. You can see that zinc 0.047, iron 0.041 and calcium 99.212, sodium 1892.44 and potassium 0.448. Similarly, sample after testing of the geotextile tube oven jute with the marine clay slurry is zinc 0.035, iron 0.030, calcium 57.43 and sodium 83.718 and phosphorus 0.01. So, percentage of removal is zinc 25.53 percentage and iron 26.82 percentage, calcium 42.11 percentage, sodium 95.57 percentage and phosphorus 97.76 percentage. Now, sample before testing tube oven jute with the fly ash slurry, zinc 0.020, iron 0.018 and calcium 99.283, sodium 92.52 and phosphorus 0.965. And sample after testing of geotextile tube, oven jute geotextile with a fly ash slurry, that zinc 0.016, iron 0.011 and calcium 39.696 and sodium 70.909 and phosphorus 0.071. So you can see percentage of removal zinc 20%, iron 38.88% and calcium 60% and sodium 23.35% and the phosphorus 92.64%. So from the test result from different hanging box tests indicate the following: the removal of zinc is in the range of 20 to 25%, removal of iron in the range of 26 to 38%, removal of calcium in the range of 42% to 60%, removal of sodium in the range of 23% to 95% and removal of phosphorus is in the range of 92 to 97%. Now this is the portion is shown the design of geotextile tube. The preliminary design of geotextile tube is reported by Liu et al. 1990 and schematic diagram of geotextile tube looks like a sausage. So this is the schematic diagram. You can see that this is the A area of the weighted soil mixture and this is the height that this the slurry is poured into this. So from this you can establish this design curve for final dimension of the geotextile strength. This is after Sylvester 1990 and Pilarisky 1997. So this is a graphical method for the determination of geotextile tube parameter is based on the research done by the Liu, Go and the Sylvester as described by the Sylvester 1990. So in this this is the pressure head and the circumferential, that is the dimensionless, that is B1 by S in the x axis, and this is the geotextile tube geometry, this also the dimension. So if it is that, if this is like a sausage type, this is the water soil mixture, this is the A and this distance is equal to B dash, because what you see in the elliptical form, when you apply load it will be in the sausage like this. So this portion is B dash and the initial it was a B, and from here to here this is the B1 and this is the H of dash and this height is equal to H. So in this also this graph which I am also showing here, this is axis is the pressure head versus circumference, that is the dimensionless, that is B1 by S. That means this is the B1 by S. So that's slurry, and this the portion geotextile tube geometry, that is also dimensionless, and this is the area. This I showed you what is H and what is B, which you can also see that this is the H and this is the B. So you can have the A by HB, you can have H by B, you can add B dash by B. Okay, that B dash means this is B dash, and this is B. So B dash by B. So all this arrow showing this curve for B dash by B. This curve shown H by B. This curve show A by HB. On the other end, this arrow indicate this is the curve. This is the curve. So this side also maybe H dash by H, B by S, H by S, and also you can have T by gamma S square. Okay. So this indicate this is T by gamma S square in this curve. Then you have to use this curve on this direction, and this is the curve B by S, means you have to take the data on this direction. While H dash by H dash curve is like this, that means you have to select the data from this side, H dash by H. And if it is a H by B, you have to select the data on this side, that means this is the curve. Similarly, if you want to select B by B dash curve, then you have to select the data from this side. If you, this is the H by S curve, if you want to select the data H by H on this side. Similarly, T by gamma S square, So this is the curve. So you have to select the data from this type. So this design chart is very helpful. So I think that you should follow that how you can take this defined value for the design of the geotextile tube. I show you here that I say that H is equal to that surface height, H dash is equal to height of the greatest width, and B1 is the pressure head, and S is equal to circumference, B is equal to width, B dash is equal to contact width at the base, A cross sectional area, T hoop tension in the fabric, and gamma unit weight of the slurry. So this is one small example. A geotextile tube has the following property: B1 is 8 meter and S is 10 meter, and T allowable is given 250 kilonewton per meter, gamma 10 kilonewton per meter cube. So determine the factor of safety as well as the dimension of the geotextile tube. So here is the solution. So when B1 by S, you know B1 is 8, S is 10, so 8 by 10, 0.8. So from the following design curve, so we can see that for B1 by S is 0.8. You can see that this is B1 by S and B1 by S is 0.8. When it is 0.8 and you require T by gamma S, this is the curve. So when B1 is this 0.8 and this is the curve T by gamma S. So T by gamma S you can move in the horizontally. So you can have this value T by gamma S is equal to 0.08. So you will have 0.08. So here also shown that T by gamma S square is equal to 0.08. Similarly, that when that means T required will be, you know that this is gamma 10 and this also the S also is the 10. So this is 10 square, then this will give 80 kilonewton per meter. So T required geotextile strength required 80 kilonewton per meter. Hence factor of safety will be equal to T allowable by T required, that means 250, that is T allowable is given, this divided by T required 80, that means 3.125 is okay. Again using the same design figure for B1 by S when 0.8. So you can calculate B1 by S is 0.8. For example, B by S is 0.33. So B1 by S is 0.8 and can show you that suppose it is 0.8 B1 by S. So this curve. So B1 by S. Okay. So this is B by S. So this is the B by S, that means this curve. So B by S in this direction. So this will give you about that 0.33. So B will be equal to 0.33 into 10, that means 3.3. Again H by S, so this is for 0.8, so H by S will be this direction. Okay, H by H is equal to 0.28 somewhere here. So H will be equal to 0.28 into 10, that means 2.8 meter. Again H by B, you can see here that H by B in this direction. So this is 0.8 H by B in this direction, that means this will give about 0.85. H dash by H, so H dash by H is this. So H dash by H is, you can move here, so you can have 0.46, that means H dash will be 0.46 into H is 2.8, that will be 1.29 meter. Again B dash by B in this direction. So B dash by B in this direction here. So B dash by B will be equal to 0.29. So B dash will be 0.29 into 3.2, then 0.96. Again that A by HB. So A by HB will be equal to 0.82 here. So 0.82 here. So this will be A will be equal to 0.82 into H is 2.8 into 3.3, it will give 7.58 meter square. So, you are having this all this value, and ultimately you have to check the for H is equal to 2.8 and B is equal to 3.3 meter, and what you are obtaining from this curve. So, you can see from this earlier this that what is H by B, you can have 0.85, okay, H is 2.8 and you can H is 2.8 and B, this is the B you can have, this is B is equal to 3.3. So, you can see H by B 2.8 by 3.3, which will give 0.85. That means from you can also check that H by B will give you that value of 8.5 here. So, you can have that H by B value, that means this is 0.85 and this is the H by B curve. So, this will give also the 0.85. So, same result you can obtain previously from the figure, and hence it is the OK. Now, the proposed design geotextile tube is almost important for coastal protection. The following information should be well known for proper engineering solution: typical wave height and the wave direction, and beach line history is very important, otherwise some structure also fail, and water depth at both high and the low tide, and the direction of the sand transport, that is by season if it is changes, and changes to the area such as sand mining or the ship grounded up, clearly define an obtainable objective. So, one has to be taken care for the proper use of the geotextile tube for dewatering for the fine grained soil, and this is also very hot area, and this is a cutting edge research topic, and many unknown like that what will be the fate of pollution in case of the hazardous material, and then what will be the microorganism in case of the biosolid, and decontamination with the geotextile tube can occur if the proper additive are including in the during the filling of the geotextile tube. So, this is very important, and one should go for the minimum 3 geotextile tube test to select the proper kind of the geotextile material for the proposed project. With this I finish my lecture today. Please let us hear from you any question, and thanks for listening.